welcome back. In our last chapter, we got our entire training environment set up and ready to go. Now it's time to get to the good stuff, choosing the right tools for the job. You see, fine-tuning isn't a one-size-fits-all kind of deal. So in this chapter, we're going to explore all the different techniques that can shape a generalist AI into a true specialist. Okay, let's dive right in. The world of fine-tuning is, well, it's huge. There's a whole universe of different methods out there, and each one has its own unique strengths. It's less like a single straight road and more like a giant branching map of possibilities.
And this is our map. What you're looking at is a taxonomy of all the different families of techniques we can use. You've got methods that add new trainable parts to the model and others that totally change how the model's weights get updated during training. Now, we're not going to visit every single spot on this map today, but it gives you a feel for the incredible landscape out there. This is going to be our guide for today's journey.
But before we even think about picking up a tool, we need a blueprint. We need a high-level strategy that answers the most important question of all. What exactly are we trying to build here? It's also really important to remember where we are in the bigger picture. This diagram is fantastic because it shows the full 7-stage pipeline for creating a specialized LLM. And we are right here, smack in the middle of stage 4. This is where all the magic happens, where we pick our technique. Everything we've done so far, getting our data ready, setting up the environment, it's all led to this one crucial choice. So the first big decision for our blueprint comes down to 2 main strategies. On one side, you have task-specific tuning. Think of this like training a specialist for one very specific job, like a chatbot that only answers legal questions, nothing else. But on the other side, there's domain-specific tuning. This is way broader. This is about making the model an expert in an entire field, like medicine, so it gets all the lingo, the context, and the subtle nuances of that whole world. Okay, so once you have your strategy, you need the right tools. And let's be real. Trying to fully fine-tune one of these massive models takes an insane amount of computing power. That's where a revolutionary set of techniques, our power tools, if you will, come into play. And this is the million-dollar question, isn't it? These models have billions, sometimes hundreds of billions of parameters. Trying to update every single one of them is just unbelievably expensive and slow. So how can the rest of us, developers, researchers, small companies, how can we possibly specialize these models without having a supercomputer in the basement? Well, the answer is parameter-efficient fine-tuning, or PEFT for short. And the idea is absolutely brilliant. Instead of retraining the whole model, you just freeze most of it. Then you only train a tiny, tiny fraction of its parameters. This, of course, slashes computational costs, but it also has this incredible side effect. It helps prevent something called catastrophic forgetting, which is when a model basically forgets all its original knowledge while it's learning something new. Now, the undisputed star of the PEFT world is LoRA, which stands for low-rank adaptation. This technique is just genius. It takes the huge pre-trained model and freezes its weights completely. They don't get touched. Then it injects these tiny trainable modules. You can think of them as adapters, right alongside the original layers. All the new learning happens inside these little modules. The key insight here is that the change needed to specialize a model is actually much simpler mathematically than the model's original knowledge. Just look at this slide. It shows the difference so perfectly. On the left, that's regular fine-tuning. It's trying to calculate a gigantic update for every single one of the original weights. It's a total brute force approach. But then look at the right. That's LoRA. The original weights are frozen. Instead, we're training 2 much, much smaller layers, A and B, and their combined result creates the update. It's not brute force, it's surgical. It's just so much smarter. And the benefits? Oh, they are huge. We're talking about a massive reduction in the number of parameters you have to train. That means way less memory, less storage space, and much, much faster training. And the best part? It adapts the model incredibly well, often getting you results that are just as good as a full fine-tuning, but for a tiny fraction of the cost. It's a real game changer. So you might be thinking, what if we could make LoRA even more efficient? Well, that's exactly what QLoRA does. It takes that big, frozen, pre-trained model and it quantizes it. It basically compresses the numbers representing the model's weights down from, say, 16 bits to just 4 bits. This absolutely slashes the memory you need to the point where you can fine-tune some of these massive models on a single consumer-grade GPU. This is what truly democratizes AI development. This table just lays it all out so clearly. You've got full fine-tuning on one end, trains 100% of the parameters, needs a ton of hardware, but gives you that top-tier performance. Then you have LoRA, trains a tiny fraction, maybe less than 1%, needs way less hardware, and the performance is still fantastic. And then there's QLoRA, training that same tiny fraction, but with an even smaller memory footprint, opening the door for pretty much anyone to get in the game.
All right, so we've covered the power tools. Now let's look at some of the more advanced, really specialized instruments in our toolkit. These are the ones you pull out for very specific and complex challenges.
So here's a fascinating problem for you. What if you need a model that's an expert not just in one thing, but in a bunch of different things, all at the same time? How do you build an AI that's a true polymath without just making it bigger and slower?
Well, the solution is this incredible architecture called Mixture of Experts, or MOE. The best way to think about it is like a team of specialist doctors. When a query comes in, a router, kind of like a receptionist, takes a quick look and figures out which specialist is the best fit for the job. Is this a poetry question? Send it to the poet expert. Is it a coding problem? Send it to the programmer expert. The key is it only sends the query to them. The other experts don't do any work at all. This means you can have a model like Mixtral 8x7b with a ton of total parameters, but you only use a fraction of them for any given task, making it incredibly fast. You know, this might be the single most important question in all of this. We can give a model knowledge and skills, but how do we teach it values? How do we align its behavior with what we humans actually prefer and make sure it's helpful, honest, and harmless? This is where preference optimization techniques come in. I like to think of them as the calibration tools for a model's behavior. Methods like direct preference optimization, or DPO, are really powerful here. They work by using datasets of human feedback. For example, you show a person a prompt and 2 different AI responses, and you just ask them which one is better. The model is then trained directly on these chosen versus rejected answers to learn the subtle patterns of what we actually want. It's that final crucial step to make sure the model isn't just smart, but that it's also aligned with our goals.
So we've looked at strategies, power tools, and specialized instruments. How do we pull all of this together? What's the big takeaway from our journey today?
You know, I think this quote just says it perfectly. The key here is to stop looking for a single best way to fine-tune an AI. It doesn't exist. Instead, you have to think of all these techniques as a toolkit. Your job is to look at the problem you're trying to solve, consider the resources you have, and then pick the right tool or combination of tools for that specific job. So let's do a quick recap of the toolkit we've put together. You start with your high-level strategy. Are you doing a narrow task tuning or a broad domain tuning? Then you pick your efficiency tool, something like LoRA or QLoRA, to save you time and money. If you need a model that can do many things well, you might look at a mixture of experts architecture. And finally, you use a calibration tool like DPO to make sure the model's behavior is properly aligned. So you've chosen your tools, you've built your specialist model, but how do you know if it's actually any good? How do you measure its performance and really validate its new skills? Well, that is exactly what we are going to cover in Chapter 7, so make sure you're subscribed so you don't miss it. Thanks for joining this explainer, and I'll see you in the next one.